In chemical thermodynamics, measurement of delta U and delta H, that is change in internal energy and change in enthalpy. Here I will be talking about the apparatus being used to calculate delta U and delta H and how do we get that amount. So first, delta U measurement. We use this apparatus which is called bomb calorimeter. Normally in numericals, if it is written that we are using bomb calorimeter, normally it will be that we are trying to calculate delta U, okay, the difference in the internal energy. And you know that when we calculate the heat supplied, okay, or heat taken out, evolved at constant volume, that is known as delta U. So delta U is nothing but Q, heat transferred, whether inside or outside, at constant volume. So what we do, that we keep the volume constant. In this apparatus, the volume of the system remains constant, and we can calculate the heat transferred by the use of this water. So we have the entire system surrounded by water. So what happens in this case, that whether heat is evolved inside the system, it will go outside to the water, and if heat is absorbed by the system, then heat will be absorbed from water. So what we can do, we can initially measure the temperature of this water, and after the reaction has completed, we can measure the reaction of this water. So depending on the amount of water, temperature of water, we can calculate how much heat is transferred from water or to the water. That heat is at constant volume, so that will give us delta U. So heat transferred either to water or from water to the system can be measured at constant volume, that will be delta U. So bomb calorimeter is sealed, volume is kept constant, heat evolved, okay, or absorbed, that is transferred to the water, can be calculated. Under these conditions, no work is done because volume is constant. So delta V is constant, it means work done will be 0. So work done will be 0, that's why delta U will be Q. This part is 0. So that's why we are saying that this heat transferred at constant volume will be delta U, because in that case W will be 0. QV denotes heat transferred at constant volume. Now delta H measurement. Delta H measurement is again when pressure is constant. Delta U we talked about when volume is constant, then heat transferred is delta U. If pressure is constant, then heat transferred is delta H, that is change in enthalpy. Measurement of this one is done in calorimeter. So this apparatus is just called calorimeter, not bomb calorimeter, okay. So measurement of heat change at constant pressure, generally under atmospheric pressure, because normally when you do reactions in test tube, it is 1 atmospheric pressure. So pressure is constant, right? In that case, it is done in calorimeter. So we know that delta H is equal to QP, means whatever heat is now transferred, that will be the change in enthalpy. So heat absorbed or evolved is QP at constant pressure, is enthalpy of the reaction. The mechanism is almost similar. What we do, we have a thermometer here. So thermometer tells us what is the temperature before reaction, what is the temperature after reaction. So on that basis, we can calculate the heat transfer. And because it is open system, why it is open system? Because pressure has to be constant. That's why it is open system. Okay. So pressure will remain constant. Heat transferred can be calculated by the use of thermometer. It will give us QP, delta H. Next is reaction enthalpy. That is change in enthalpy of entire reaction, delta H. A balanced chemical equation together with the value of its delta H of the reaction. Delta RH means enthalpy change of whole reaction is called thermochemical equation. So what is a thermochemical equation? Thermochemical equation is that reaction, equation of that reaction in which either heat is transferred or heat is absorbed, means either it is exothermic reaction or it is endothermic reaction, then it is thermochemical equation. If there is no heat change, obviously there is no temperature involved, we won't normally refer it to as thermochemical, delta H will be 0. So depending on whether the reaction is endothermic or exothermic, delta RH can be positive or negative. For endothermic, heat is absorbed, it will be positive. Okay, so endothermic heat goes into the system, so it is positive. In exothermic, heat goes out of the system, means it is negative. Endothermic, exothermic, remember, positive and negative. Example: carbon dioxide dissociates into carbon monoxide and oxygen, and here delta RH is positive. If it is positive, means heat is going into the system, it is endothermic. Now this one, when alcohol reacts with oxygen, it gives us carbon dioxide and water. Here the delta RH is negative, means heat is going out of the system, it is exothermic. So this one is endothermic, this one is exothermic. Reaction enthalpy, again the same thing, the change in the enthalpy, the change in the heat at constant pressure, QP. That's what we are talking about, reaction enthalpy. It can be given by the sum of enthalpies of product minus sum of enthalpies of reactant. I'm just going back to explain it. Suppose I am talking about the second equation here. So what is changed? Suppose here you have H1, the sum of these enthalpies H1, and here you have sum of enthalpies as H2. So what will be delta H? Delta H will be final minus initial. That's what we are talking about here in this particular formula. We are saying final means products enthalpies, add all those, sum up. Okay, reactants enthalpies, add all those, and the difference will give us delta H of the reaction. Okay, why we have AI and BI? This is actually, we need to consider how many moles are there. Okay, so if I go back again, here I have to consider that I have 3 O2, means whatever enthalpy will be for 1 mole, I have to multiply that by 3. So that's why AI and BI represent these stoichiometric coefficients. Okay, here it will be 1. If it is not written, it will be 1. So here AI and BI are respective stoichiometric coefficients. AI stoichiometric coefficients of products, BI stoichiometric coefficients of respective reactants. Okay, so for in this case, suppose I will first consider this one, products, this one. Okay, so whatever will be the enthalpy of formation here, remember here I will be using enthalpy of formation. Enthalpy of formation of CO2, I will multiply that by 2. Then I will add enthalpy of formation of water multiplied by 3. That will be this part. Okay, for reactants, enthalpy of formation sum, I will use just 1 mole of this one, enthalpy of formation. So suppose I write it as C2H5OH. Okay, it will be given to you. Then I will add 3 times enthalpy of formation of O2. That will give me this part, and their difference will tell me the enthalpy of whole reaction. So stoichiometric coefficients 1, 3, 2, 3 you have to consider, otherwise your answer will be wrong. And formula is very simple to calculate the enthalpy of the reaction. Okay, so these values will be given. Enthalpy of formation of C2H5OH, enthalpy of formation of O2 will be 0. Okay, if you see any component here in elemental form, okay, so oxygen exists as O2, its enthalpy of formation will be 0. Remember, there must be only one element, only one. You can't say it is CO2. Okay, so suppose you have H2, enthalpy of formation 0, Cl2, enthalpy of formation 0, O2, enthalpy of formation 0, O3, ozone, enthalpy of formation 0, because oxygen exists as O3 as well. Okay, so O3 also 0, O2 also 0. If you have enthalpy of formation of iron, 0. Okay, solid, in solid form. Enthalpy of formation of aluminium, solid form, 0, because it exists like that in elemental form, only elements. Okay, standard enthalpy of reaction. Standard enthalpy is that when we talk about normally at 1 bar pressure, room temperature and 1 bar pressure. When it is room temperature, sometimes we call it reference value as well. Okay, so standard state is 1 bar. So if we are calculating the enthalpy, change in enthalpy delta H at 1 bar pressure, then instead of calling it just delta RH, we say delta RH naught. This naught represents standard, means it is at 1 bar pressure. So even if the pressure is not given, you must know that if you have to use, you will use 1 bar. For example, for this reaction, delta RH will be what? It will be sum of, this is something I have already explained, it will be sum of the enthalpies of products multiplied by their respective stoichiometric coefficients. So here CO2, you have only 1 mole. So it will be just enthalpy of formation of carbon dioxide, and you won't multiply it by something because it is just 1. Okay, the stoichiometric coefficient is 1. Here it is written M means molar. Okay, M represents molar, but normally in questions you will get it written as HF, enthalpy of formation. Then 2 times enthalpy of formation of water. So enthalpy of formation of water multiplied by 2. Remember, this form represents just its state. So carbon dioxide in gaseous form, you don't need to write in your exam, right? It is just for explanation. Minus enthalpy of formation of the reactants. So reactants, you have 1 mole of methane. So obviously enthalpy of formation of methane in gaseous form, and then plus 2 times the enthalpy of formation of oxygen. HM is molar enthalpy of formation. So that's why M is written, but normally F will be written there. So that's what I have written. Normally delta FH will be there instead of HM. So in standard enthalpy of formation, what is this enthalpy, standard enthalpy of formation? Okay, I have been talking about. So the standard enthalpy change for the formation of 1 mole of a compound. But there is a caveat. The condition is the elements have to produce the compound. So you cannot say calcium oxide, that is quicklime, combines with CO2 and gives you CaCO3. Here you are getting 1 mole of calcium carbonate, but it is not a reaction to represent the enthalpy of formation. Okay, so it will not give you delta FH of this reaction. The reason is, as per the definition, calcium carbonate 1 mole has to be formed. Okay, it is in solid form, their standard form. Okay, reference state, standard form. Have to be formed, this has to be formed by its elements. What are the elements? Elements are calcium, carbon, oxygen. So if you use calcium plus carbon plus O3, O3 means if you use O2, you have to use 3 by 2 O2. 3 by 2 into 2 will give you 3O. Okay, 2 will get cancelled. So you have to use O2. You don't have O. Oxygen does not exist as O. Oxygen exists as O2. So that's why you have to use here 3 by 2 so that you have 3 atoms. This represents the enthalpy of formation, because you are getting 1 mole from its constituent elements which are in their standard form. Okay, these elements must be in their standard form. Okay, which is also known as reference state if it is room temperature, also known as reference state. Now another important point, sometimes the reaction is written. So for example, the reaction will be given like 2C plus 2O2 gives you 2CO2, and here you see this is in elemental form and it is in solid form. It is given. Okay, it is given in gaseous form, this is in gaseous form, so all are in reference state. Okay, and you say that it is the enthalpy of formation. No, the condition is also of 1 mole. Okay, 1 mole has to be there. So this actually represents for 2 moles. So delta FH will be here half of it. So suppose delta RH is given, enthalpy of this whole reaction is given X. then delta FH will be half of delta RH, because for that you have to produce only 1 mole, not 2 moles. Okay. So reference state is 1 bar pressure, which I told you earlier also, that is the standard state. If it is at room temperature, room temperature is 25 degrees Celsius, it is known as reference state. So for example, the reference state of dihydrogen is hydrogen gas, those of dioxygen, carbon and sulfur, oxygen gas, C graphite. This is important to remember. Carbon standard state is graphite, not coke, not diamond, okay, not fullerene. You might have heard about the various forms the carbon exists in. Only graphite is the standard form. So if it is written in the reaction CS, normally we will consider it as C graphite, carbon graphite. That is the standard state. Sulfur exists as S8. Okay, so rhombic form of sulfur is standard form. Note that enthalpy change for following reaction, this is something I have already told you. It is not the enthalpy of formation. The reason is very simple. These are not in elemental form. Okay, you have to have these in elemental form. This is the enthalpy of formation. Example, enthalpy of reaction. Consider the calculation of heat of reaction for the following. Here the Fe2O3 reacts with hydrogen, gives you iron and H2. Delta F of H2O means enthalpy of formation of water is given. Enthalpy of formation of Fe2O3 is given. Enthalpy of formation of iron will be 0. This is something I have already told you, that all elements in their standard form will have enthalpy of formation 0. And then enthalpy of formation of hydrogen will also be 0. So in this case, these two enthalpy of formations will be 0. So if you calculate the enthalpy of this particular reaction, it will be the sum of enthalpies of products minus sum of enthalpies of reactants. We will use that formula. Okay, so we will add the enthalpies of formation of products. So 2 times enthalpy of formation of iron, which obviously is 0. Okay, then 3 times enthalpy of formation of water, then reactant side enthalpy of formation of Fe2O3, and 3 times enthalpy of formation of hydrogen, which obviously is 0. So substitute these values, get the answer. So enthalpy of this particular reaction you can get very easily by using the formula. It will be minus 33.3 kilojoules per mole. Then enthalpy of reverse reaction. Enthalpy of reverse reaction will be just opposite the sign. So if it is positive, reverse reaction enthalpy will be negative, same amount. If it is negative, reverse will be positive, same amount. Okay? So when a chemical equation is reversed, the value of delta RH, that is enthalpy of reaction, is reversed in sign. Sign changes, that's it. So suppose this is the reaction of enthalpy of the reaction for formation of ammonia, right? Remember, it is not for 1 mole, so it is not enthalpy of formation. In this case, it is not enthalpy of formation because it is 2 moles, but yes, it is enthalpy of this reaction, whatever is given. So suppose now if you have the reverse reaction, ammonia dissociates into nitrogen and hydrogen. It is opposite, okay? Then it will be plus 91. So whenever you see the reverse reaction, you will change the sign.